So today we're talking about some linear algebra. So that's do something about it. So our first section is dealing with linear equations. So let's change the color of the pen. I always forget to fix the thickness of the pen. Okay. So in linear equations, we're talking about exactly that, lines. And of course, we are certainly at this point familiar, but in case we forgot, you know that all equations can be written in this form. Right? This is the standard form of a linear equation. Of course, where A, B, and C are elements of real numbers. So, and of course, as well, you know that A or B is not going to equal 0. Very good. So this is, of course, your very famous equation from your algebra classes, which you learned many, many decades ago, I'm sure. And as such, we can extend it also to include 3 variables. To have a line in 3 variables, if it looks something like this, it would be and of course, we either have A, B, C is equal to not 0, A, B, or C. It doesn't matter. One of them cannot be 0. And of course, in this situation, we have A, B, C, D are elements of real numbers. Okay. Now, I could have as many variables as I want in a linear equation. Doesn't matter. As long as one of the variables involved is not 0, and everybody has degree 1. Okay. And so, we extend this to give a formal definition of linear numbers. So let's give this definition. Let's give a definition. For that, we'll change the color of the pen. So definition. It is just a fancy wording. We have given a positive integer n, the general linear equation in x sub 1 all the way to x sub n is da 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 da. So, give it a positive integer n. It was general equation, not solution, by the way. I copied it from the text wrong. Okay. So I will read that fancy definition and then I will translate it for you. Definition of linear equation is given any positive number n, the general equation for x sub 1 all the way to x sub n is a sub 1, x sub 1 plus a sub 2, x sub 2 plus dot 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 all the way to a sub n. X sub n is equal to b, where a sub 1 through a sub n and b are all elements of real numbers, and at least one of a sub 1 through a sub n is not equal to 0. Okay. In other words, what I'm saying is, with the linear equation, I have to have a few things. Okay? I'll write the characteristics down in a way that you'll understand, in a way that you'll remember it. Alright, the characteristics. 1. All variables, which are the x's, must have degree 1. So you see all the x's in this equation have degree of 1. Other thing that you're going to see right? Right. The second characteristic, there has to be at least one non-zero term. That is to say, you can't have a line if you don't have a term to work with. So if it have 0 equals 0, it's a point, not a line. Okay? We'll discuss why that is later. But there has to be at least one non-zero term in a linear equation in n variables. Okay? Those are the characteristics which you need to know about it. Now, why we use x sub 1, x sub 2, x sub n? It orders our variables. So x sub 1 refers to the first variable, x sub 2 refers to the second variable, all the way on and so forth. So it gives us an order. This is why we don't use x, y, z, t, and don't continue on and on. Plus we use these letters, these variables for other situations, like t is for time or something, s for arc length, d for electrical displacement, things like that. So why we use x sub 1 next year? So if you get mad at me for using x1 and x2 and all these things, too bad. Deal with it. So we of course can use linear equations for all kinds of things. So my first example will be how do we distinguish a linear equation, and then we'll apply it. Okay. So we ask, are the following linear equations? So we'll deal with these three equations and we'll deal with some implications. Now, the first question here. So the first problem that I want to look at is part A. Part A is relatively obvious, but if you don't see it, that's okay, then don't worry. We'll point it out. So A, what do we see? We know that 5, 1/2, negative 1/2, and negative 3 are elements of real numbers. So first thing we need to do is rewrite it in terms of x, y, z, in terms of our equation. So we can let using our x2s and x3s to order our variables, even though we don't have to do this step, but you're going to be using x2s and x3s for most of your time, so I want you to get used to it. So, and then x is equal to x1. So that just becomes 5x1 minus 1/2 x2 equals 3x3 minus 2. And if I rewrite it, I end up with 5x1 minus 1/2 x2 minus 3x3 is equal to negative 2, which I can leave, and I would say that yes, this is a linear equation. Why? Because 5, negative 1/2, and negative 3 are, of course, elements of real numbers, and along with the negative 2 is real numbers. So this is a linear equation. So we say yes. For part B, it's a little bit tricky. Alright, so for part B, we have x cosine of 2 minus y sine of 3 is equal to, oops, my bad, I did not mean to add a page. To go back a page. Plus y sine of 3 is equal to pi. This should be sine of 3. Okay. Of course, sine. Now, if the x was inside of this, if the x was inside and the 2 on the outside, it wouldn't be linear. But because the x is on the outside, cosine 2 is just a constant. So, again, we can treat it, we can let a is equal to cosine of 2. Let a1 equal cosine of 2. Let a2 equal sine of 3. And of course, x1 equal x, x2 equal y. This becomes a1 x1 plus a2 x2 is equal to pi, which of course is a linear equation. Oh my god, my handwriting's horrible today. Yes, it is a linear equation. For part C, going back a page, we have 3y minus 5 is equal to 2x divided by z. of course, we have to manipulate this equation. So we let x equal x1, y equal x2, z is equal to x sub 3, and then we're going to multiply both sides by x3. Multiply both sides by x3. So thus, we'll rewrite it first. We do it with 3x2 minus 5 equal to 2x1 over x3. Multiply both sides by x3. We end up with 3x2 x3 minus 5x3 equals 2x1, which is of course not a linear equation. Why? Because as you can see here, these two get multiplied, and you can only have one in that situation. You can only have one variable. Linear equation, by its own definition, has one. So this is not a linear equation in part C here. Okay? And since this section's relatively simple, that's about it. We can apply this in certain situations, and I would like to do an application involving this particular point. So, an application problem, there's thousands of different applications we can use for this problem. So let's do a physics problem, a physicist. So we'll do a physics problem. Oops. Okay, so here's another example. So we have an example. We have mass. We have 3 masses on a fulcrum. Or 3 masses on a lever, something like that. Let's draw your picture. That's about as good of a straight line as it's going to be. This is center of, it's kind of your fulcrum or the pivot point. So over here we have M3. And from M3 back to the lever is distance x1. Or x3, sorry. Then you have another distance here, we'll call that m1. And the distance from it to the center is x1. Of course we have here m2. And the distance from here to there is x2. Supposed to be straight lines, but you'll have to deal with my horrible drawing. So the question they asks us is, what condition must be satisfied in order for the system to be in equilibrium? The question they ask is, what condition must be satisfied system be in equilibrium that it asks, is it linear for x1 to x3? So it asks, is it linear for its masses, for the distances, or the radiuses? And it asks, is it linear for both? Okay, that's the question that they're asking us. Now, at this point, you're all mathematics majors and of course should have taken some sort of physics class. But I'm sure you're falling asleep during physics classes for a lot of you, because you said, oh, physics is boring, we're not going to use it at all. But physics is, of course, the study of laws of nature, and it's very beautiful, and we use it so much, and we use math so much to help us understand the universe. Yes, I'm going to make you do lots of physics examples by the time you're through with this. So, looking at the question, we need to understand what the hell it's talking about. It's firstly talking about equilibrium. Equilibrium is when what happens? Equilibrium is when the vector sum of forces is equated to, well, nothing. Equilibrium is in balance, okay? In the same. No. Sounds familiar, doesn't it? I'm sure it does. Okay. Now, there's two types of equilibrium. And of course, I don't really have to explain this. I could just do the math, but I'm a physicist by trade, so I'm sure as hell not going to let you get away without knowing physics. So, equilibrium speaks of two particular points. Okay, we have one point when the vector sum of forces, external forces, is added to 0. This is one type of equilibrium. This is Извините меня, пожалуйста. I'm still recovering from this annoying runny nose, and it's driving me nuts, but it's okay. Okay. That is one type of equilibrium, and when we speak of this, sometimes it's called static equilibrium. Sometimes it's called static equilibrium. There's other names for it as well. There's another type of equilibrium where the vector sum of torques is added to 0. And we use capital gamma, sometimes lowercase tau for it. Okay. Forces is when you're pushing and pulling and it all cancels down to 0. Torques is when you're twisting, rotating, turning, and it adds to 0. Right? So in those situations, these have to be 0. And interestingly enough, you have nothing. You have something that's given for neither of them. Okay? So you have two types of equilibrium, which I just had to tell you, so you understand what the hell they're talking about. Now we can go about solving the problem. So we'll solve letter B. You can do A and C on your own. So to set this up, right, so to set this equation up, we will do it like that. Okay, we know that everything has to add to 0. So we know one of these two equations has to. We know they both have. And in a situation where we have full and total equilibrium, both would be true. So we're not going to worry about that so much because this example is extremely simple. So how we work it is really simple. So the total forces need to add to 0. So in this situation, I have, right, we'll deal with, actually the torque situation is easier to work with. So torque is here Let's go to the next page. Actually, let's go to the next page. So torque is, of course, radius times its force. In this situation, force is not given. And for that matter, neither is any, so we need to get rid of it. Since force is not given, a radius can be defined as your x1, x2, and x3. So, since force is not given, I have to rewrite it. Using Newton's second law, the acceleration of a body is a vector proportional to its force and inversely proportional to its mass. I can then, from there, say the sum of forces is mass times acceleration. Right? I can't substitute it straight because it's not definition. Okay, this is the law. This is the law. And if you ever told otherwise, have your teacher just slap you upside the head. Because this is correct, this is not. We'll speak more of that in my physics lecture. So, now, if I can do that, I can take this and replace it with that. Of course, A is not given either, but A will end up canceling. And I'll show you how in a minute. So now, what I end up with is a situation like this. R times M times A, which will be rewritten as X to the N times M to the M times A. Okay? Which, of course, this will end up being 0. So I'll show you how it goes away a little bit here. Okay, so back to our fancy equation, back to our fancy board, which is over here. Okay, so this times this plus this times that, plus this times that, all has to equal 0. So watch how this works. Alright, don't worry about this A piece, but it's going to end up going away shortly. So I rewrote this radius as this, and I wrote M as this. So now I know that the sum of all these must equal 0. So therefore, I have x3, m3, plus a. A stands for acceleration, but we're going to end up eliminating it in a minute. And then it ends up being plus x2 m2a plus x1 m1 a is equal to 0. A is the same. Why is it the same? Because this is a system, so they're moving together. And because they're moving together as a system, they're going to collectively undergo the same acceleration, even though they're at different distances. Okay? And of course, in this situation, the acceleration is 0. So the a factors out from this equation. So you know what 3 equals 0. A goes away. So you end up with the equation that you need. So this is the equation that you need. We'll rewrite it. x1 m1 plus x2 m2 plus x3 m3 is equal to nothing. And so it asks the question, is it linear in x? Is it linear in x? Yes, because m1, m2, and m3 are constants. And of course we know the only way that mass can be 0 is if it's not a body. Okay? Something does not have the capability of having mass, like light. But we'll see that later. Now, so we'd say, so letter B is yes. And for the matter letter A, it's also yes. Why is A yes? Because mass is linear, right? Mass, right? In this equation, the radius would be constant. And of course, part C in this equation, we know they're not, because it's under. If they're under both, they're being multiplied, and that would not make it a linear equation. Okay. right? You cannot have a linear equation if you have two things changing at once. Right? If you have more than one variable in that situation. If you have more than if you have one variable, it gets a lot easier to work with. But if you have two variables you multiply, then it will not be linear. Okay? Alright. So oddly enough, that is section 1.1. Not really much to be talked about. Other than this, really. This. But one more thing I want to mention is about parameters. Parameters is, of course, when you have more or when you have more variables than equations or something like that. Okay. When you have more variables than the number of equations, that's what you have for parameters for. It says that's so we'll define parameters really quickly and then we'll do something like that. So to define a parameter, is a variable used to define another variable. Okay, simple enough. So, and I only use parameters when what? I have more equations not more equations, more variables than equations. If you have more equations than variables, that doesn't matter. Alright? When I have more variables than equations. Why is that important to understand? Okay? No, it's simple, really. Right? The idea is you have too much of something. Because you have too many equations, because you have too many variables in that situation, you gotta make your life easy. You can only have, right, the number of equations dictates the number of solutions. And since you have more equations and variables, then you're going to have an infinite amount of solutions. So let's work with how to define a parameter. So let's define a parameter. So let's start with a simple equation. Let's start with an example. How do I define a parameter? Okay. And it's 3x. Alright. So in this situation, excuse me. So in this situation, I have to pick a variable to solve for. It does not matter which equation I solve it for. I can define a parameter in terms of any variable I wish. Sometimes certain variables make it easier than others, but I can define it for any variable I want. It really doesn't matter. It's subjective. So I have to solve this equation that I have up here, that I'm pointing out with the cursor, for a variable. So solve for a variable. Doesn't matter. Pick one. X, Y, Z. You know, I like to keep our x's by ourselves. Let's solve for x because, well, x's should be kept far away from people at all times. At least in the vast majority of situations. And I can't speak to your own situations, but I can definitely speak to a couple of situations in my own life. Yeah, those people need to stay far away. Too much too painful of an experience. So I'm going to choose x. So to solve everything for x, we'll do this. Since you guys are algebraic masters at this point, you already will know that 3x is equal to 3z minus 5y. Divide by 3, you end up with x equals z minus 5/3 y. Right. From here, right, we have x as the equation. And then since from here we have our equation to work with, now that we have to set it in terms of two parameters, in this case, we have I can define the parameter. You can define z and y to be the parameters in this situation. Again, I could have chosen any variable. I could have solved for y, I could have solved for z, but I like to isolate my x's. So I'm going to define thank you. Define y to equal s and z to equal t. These will be our parameters that we will work with. Alright. So if I define y to be s and t, let's rewrite the equation. So we end up with x equals, going back a page, so we end up with x is equal to t minus 5/3 s. Right. The key to the parameters is that we define them. So x is equal to t minus 5/3 s. And because x is equal to this, t, we write every answer in terms of their parameters. So every answer for x, y will be written in terms of the parameters. So the solution here you end up with the curly brackets here. And then you end up with x, which is t minus 5/3 s. Y is, of course, s. Z is, of course, t. And, of course, it's based on the condition that s and t are elements of real numbers. So that's our solution set. everything is defined in terms of the parameter. So it is important when you're looking at parameter equation to define all things in terms of your parameters. So all or in this case, all your variables, of course. Now, and that is pretty much it on section 1.1. They do a bunch of different examples with like population growth, but I don't care about any of that. So we're not going to do that. But the same rules will apply to the harder examples of physics, because I like those ones. So next section we'll discuss in 1.2, we'll talk about systems of equations and the strategies involved with that.